Beneath the starry chaos, a secret order waits to be read. The universe hums with a hidden code, from the spin of a galaxy to the dance of the smallest particles. We are about to embark on a journey through 30 mind-bending theories that attempt to crack this cosmic cipher. You will discover how the fabric of reality might be a hologram, why time itself could form crystals, and if our entire existence is just an advanced simulation. Are the strange motions of distant worlds pointing to a missing planet in our own solar system? And does the eerie silence from the cosmos mean we are truly alone? What single idea about the universe most captivates your sense of wonder? The first clue in this cosmic puzzle is a number sequence scribbled in the margins of a 13th century manuscript. 1, 1, 2, 3, 5, 8, 13, 21. This is the Fibonacci sequence, a simple pattern where each number is the sum of the two before it. But this is no mere mathematical curiosity. It is a secret code that nature seems to have written into the very fabric of existence. You can find it in the elegant spiral of a nautilus shell, where each new chamber grows in perfect proportion to the last. It is in the head of a sunflower, where seeds pack themselves in opposing spirals, their counts always landing on consecutive Fibonacci numbers. It is even in the way branches grow from a tree trunk, or leaves arrange themselves around a stem, each seeking its own space in the sun. This pattern is not confined to our planet. Look at the vast whirlpool of a hurricane seen from space, its spiral arms tracing the same logarithmic curve. Peer into the depths of the cosmos, and you will see entire galaxies, like the majestic Pinwheel Galaxy, spinning in that same familiar, elegant spiral. All of these forms are connected by a single, irrational number known as the golden ratio, approximately 1.618. This ratio, often called phi, is what you get when you divide a Fibonacci number by its immediate predecessor. As the numbers grow larger, the result gets closer and closer to this magical proportion. It is a ratio that the human eye finds inherently and mysteriously pleasing, a building block of beauty from the Parthenon in Greece to the Mona Lisa's smile. So why is this pattern so universal? Is it just a cosmic coincidence? One compelling idea is efficiency. In a sunflower, the Fibonacci spiral is the most effective way to pack the most seeds into the smallest space, a masterclass in natural engineering. For plants, arranging leaves in this pattern minimizes shading, allowing each leaf to catch the most sunlight. This points to an evolutionary advantage, a slow, silent optimization over millions of years. But when we see the same mathematical rule governing the curl of a fern and the spin of a galaxy, it forces a deeper question. Are we simply seeing the most efficient solutions arising independently? Or is this numerical signature evidence of a fundamental design, a single, elegant equation from which all of reality unfolds? This same mathematical elegance seems woven into the very largest structures of the cosmos. But to find its source, we must listen for a whisper from the dawn of time. That whisper is the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. In the 1960s, two astronomers accidentally discovered this microwave static coming from every direction in space, a uniform bath of heat that has been cooling for nearly 14 billion years. This discovery was monumental proof that our universe had a hot, dense beginning, but it presented a deep mystery. Why was the temperature of this primordial light so incredibly smooth from one patch of the sky to another? Regions of space now on opposite sides of the visible universe had the same temperature, yet according to the standard laws of physics, they could never have been in contact to equalize their heat. It was as if two strangers on different continents were wearing identical outfits without ever having spoken. The most compelling solution to this puzzle is a theory called cosmic inflation. This proposes that in the very first fraction of a second after the Big Bang, the fabric of spacetime itself underwent a burst of hyper-accelerated, exponential expansion. The universe did not just expand, it inflated, stretching from a subatomic speck to a vast cosmos faster than the blink of an eye. This violent stretching smoothed everything out, explaining the remarkable uniformity we observe in the cosmic background. But inflation did more than just iron out the wrinkles. It also created the seeds for everything to come. Even in that primordial void at the quantum level, there were tiny, inevitable fluctuations, a faint fizz of virtual particles popping in and out of existence. The incredible force of inflation stretched these microscopic ripples to astronomical sizes, imprinting them as minute differences in temperature and density onto the fabric of the young universe. These tiny imperfections, frozen into the cosmic microwave background, are the cosmic blueprints we can still read today. The slightly denser spots, revealed by ever so slightly warmer patches in the microwave sky, became the gravitational anchors that slowly pulled in matter over billions of years. They are the reason galaxies formed where they did, the reason galaxy clusters exist, and ultimately the reason we are here to observe them. The pattern of the cosmic microwave background is not just a relic, it is the universe's first and most important fingerprint, the foundational code from which all structure emerged. Yet even that cosmic fingerprint, that grand blueprint from the beginning, might itself be a projection of something far more strange and two-dimensional. The holographic principle is one of the most radical ideas to emerge from theoretical physics, suggesting that all the information describing our three-dimensional reality, every star, every planet, and every one of us, might actually be encoded on a distant two-dimensional surface. Think of the shimmering hologram on a credit card. That seemingly three-dimensional image, with its depth and perspective, is not truly three-dimensional at all. It is a flat surface containing all the information necessary to create the illusion of a solid object when light strikes it in the right way. The holographic principle proposes that our entire universe operates on a similar, but vastly more complex scale. The origins of this mind-bending concept lie in the paradoxical nature of black holes. When matter falls into a black hole, it vanishes behind the event horizon, a point of no return. But a fundamental law of physics states that information cannot be destroyed. So where does the information about that matter go? Theorists like Jacob Bekenstein and Stephen Hawking explored this puzzle and found a startling answer. They discovered that all the information about what falls into a black hole could be entirely encoded on the surface area of its event horizon, the black hole's two-dimensional boundary. The entire contents of a three-dimensional volume are somehow painted onto its two-dimensional surface. This realization led other physicists, like Gerard T. Hooft and Leonard Susskind, to ask a breathtaking question. If this is true for a black hole, could it be true for the entire universe? Could the cosmos we inhabit, with its vast, three-dimensional expanse of galaxies and nebulae, be nothing more than a magnificent holographic projection? The theory suggests that the true, fundamental laws of physics are written on a thin, distant shell that surrounds us, a cosmic film containing the code for everything we see and experience. The three-dimensional world, with all its richness and texture, would then be an emergent illusion, a hologram of stunning complexity. This idea shatters our most basic assumptions about space and reality. We feel the solidity of the ground beneath our feet. We move through a world of depth and volume. Yet the holographic principle whispers that this is all a magnificent shadow play. It forces us to confront a dizzying possibility. Are we and everything we know just a ghostly image projected from the edge of spacetime itself? This same principle of a hidden code finds an even more intricate expression in the language of fractals. A fractal is an infinitely complex pattern where the same beautiful, irregular shape repeats itself at every scale. Zoom in on a tiny piece of it, and you will find a structure that looks just like the whole. The most famous of these is the Mandelbrot Set, a mathematical island of infinite complexity born from a deceptively simple equation. When you explore its boundary, you find an endless cascade of detail. Majestic, seahorse-like spirals give way to smaller spirals, which themselves are covered in tiny, thorny tendrils. Every zoom reveals new worlds, each a distorted echo of the one before, a universe of patterns within patterns that never, ever ends. And this is not just abstract math. Look at a photograph of a lightning bolt. Its main trunk splits into branches, which split into smaller forks, all tracing a fractal path through the sky. Examine a coastline from space. Its rugged inlets and peninsulas are not smooth curves. If you were to walk its entire length, you would find that every bay has smaller bays, every headland has smaller outcrops. The measured length of a coastline actually increases the closer you look, a direct result of its fractal nature. You see this same pattern in the branching of trees, the intricate network of our own blood vessels, and the jagged silhouette of a mountain range. These are all examples of nature speaking in a fractal dialect. The most profound application of this idea suggests that the universe itself might be fractal on the grandest of scales. When we map the distribution of galaxies, we do not see a random scattering. Instead, we find a cosmic web. Galaxies cluster into groups, which are part of larger superclusters, which themselves form immense filaments and walls stretching across billions of light years. This vast structure, with its dense nodes and empty voids, bears a striking resemblance to the neural networks of a brain or the frothy bubbles in a sink. If this pattern holds true at scales both larger and smaller than we can currently observe, it implies a cosmos of infinite regression. There may be no fundamental smallest scale or largest scale, only an endless nesting of complexity. Are we living inside a fractal, a single layer in an infinite cosmic tapestry that has no beginning and no end? This precise fine-tuning of the cosmos leads us to a deeply personal and profound question. Why does the universe seem so perfectly tailored for our existence? This is the core of the anthropic principle, the idea that the fundamental laws and constants of physics appear meticulously calibrated to allow for life. Consider the force of gravity. If it were just a tiny bit stronger, the universe would have collapsed back in on itself in a fiery crunch moments after the Big Bang. If it were slightly weaker, matter would have flown apart so rapidly that stars and galaxies could never have coalesced from the primordial gas. The strength of the nuclear forces inside atoms is just as precarious. If the strong nuclear force, which glues atomic nuclei together, were even a fraction of a percent different, protons would not stick to neutrons. Stars would be unable to forge the carbon and oxygen that are essential building blocks for planets and life. The very atoms that make up our bodies would be impossible. We find ourselves living in a universe where dozens of these fundamental numbers, from the mass of an electron to the energy of empty space, are set to values that fall within an astonishingly narrow, life-permitting range. It is as if a cosmic architect adjusted countless dials to their exact, perfect positions. The simplest interpretation of this incredible coincidence is known as the weak anthropic principle. It states, quite logically, that we can only observe a universe that is compatible with our existence as observers. In an infinite variety of universes with different physical laws, we obviously find ourselves in one of the rare ones that allows for stars, planets, and biology. We are here, so the universe must be built in a way that allows us to be here. It is a cosmic selection bias. Yet for some, this simple observation is not enough. They propose a more daring idea, the strong anthropic principle. This version suggests that the universe must, in some fundamental way, have properties that allow life and consciousness to arise. This is a far more controversial statement, as it hints at a sense of purpose or design woven into the fabric of reality. It pushes the question from a simple observation to a profound mystery. Why must the universe be life-friendly? One compelling answer to this riddle does not require a single, fine-tuned universe, but rather an almost infinite multitude of them. This is the concept of the multiverse. In this vast cosmic landscape, countless universes bubble into existence, each with its own random set of physical laws and constants. In the overwhelming majority of these universes, the numbers are all wrong. Gravity is too strong, atoms are unstable, and cosmic history is brief and barren. But in a vanishingly small number of these bubbles, like our own, every dial lands in the perfect place. We do not live in a specially designed universe. We simply live in one of the rare, habitable islands in a chaotic, infinite sea of possibilities. The eerie fine-tuning is not a miracle, but a statistical inevitability given enough chances. This idea transforms our place in the cosmos. Are we the intended outcome of a grand cosmic plan, or are we simply the lucky winners in the ultimate lottery, living in the one universe where the numbers lined up just right? But this cosmic lottery of the multiverse raises a profound question about the nature of reality itself. If we are just one possibility among an infinite sea of others, how solid is the world we perceive? The answer may lie in the bizarre and counterintuitive realm of the very small, where the universe reveals a hidden web of connection that defies all common sense. Albert Einstein famously dismissed a core quantum phenomenon as spooky action at a distance, a phrase that perfectly captures its unsettling nature. This is the puzzle of quantum entanglement. Imagine a pair of particles born from the same event, perhaps two photons created simultaneously. These particles become linked or entangled. Their properties, like their spin or polarization, are not defined individually but exist in a shared, fuzzy state of potential. They are a single quantum system, even if they are later separated. The truly mind-bending part occurs when you measure one of them. The instant you observe the spin of the first particle, forcing it to choose a specific state, its distant partner, even if it is now on the other side of the galaxy, instantly snaps into the corresponding opposite state. This connection is instantaneous, seemingly faster than the speed of light. This is not a signal being sent. It is a fundamental, immediate update to the system. One particle somehow knows what happened to its twin, defying our classical understanding of how information and influence should travel through space. This challenges the very idea of locality, the principle that objects are only influenced by their immediate surroundings. Entanglement suggests that the universe at its most fundamental level is non-local. What we perceive as separate, distant objects can be intimately linked in a way that transcends the space between them. How is this possible? One compelling theory is that this interconnectedness is not some strange signal flying through space, but a feature of spacetime itself. The entangled particles are not communicating, they are simply manifesting a deeper, underlying unity. Think of spacetime not as an empty stage, but as a single, woven fabric. Two particles might appear distant on the surface of this fabric, but if they are connected through a hidden fold or a deeper thread within the weave, their fates are bound as one. They are not two separate entities sending messages. They are two visible expressions of a single, deeper object. This suggests that what we perceive as empty space is teeming with a hidden architecture of connection, a cosmic web of entanglement that links every part of the universe. Every interaction that has ever occurred may have left behind a faint quantum thread, tying the past to the present, and linking you to the most distant star. The solid, separate reality we experience may be an illusion, a surface appearance over a profoundly unified whole. Are we, like the entangled particles, simply individual expressions of a single cosmic pattern, forever connected across the vast expanses we see? This infinite web of connection hints at a cosmos of unimaginable scope, one where our entire universe might be just a single bubble in a boiling sea of realities. The theory of eternal inflation paints this breathtaking picture. It suggests that the hyper-accelerated expansion that smoothed our infant universe never actually stopped. Instead, the inflationary energy of spacetime acts like a constantly boiling pot of water. Most of this primordial energy continues to inflate at an incredible rate, but here and there, random quantum fluctuations cause pockets of that energy to settle down, to cool and crystallize into stable spacetime. Each of these settling pockets becomes a big bang in its own right, giving birth to a separate bubble universe. Our entire cosmos, with its hundreds of billions of galaxies, is just one such bubble adrift in an eternally inflating meta-universe. The truly staggering implication is that each of these bubble universes could have its own unique set of physical laws and constants. The strength of gravity, the charge of an electron, even the number of spatial dimensions might be randomly determined when each bubble forms. In an endless ocean of such bubbles, most would be stillborn, with laws too hostile for any complex structure to ever form. But by sheer, unimaginable numbers, a few bubbles like ours would inevitably have the perfect combination for stars, planets, and life. This is how eternal inflation answers the riddle of the Holographic Principle. We do not live in a universe fine-tuned for life. We live in one of the infinitesimally rare universes where the random dice roll produced a habitable world. This cosmic inflation is just one version of a multiverse. Another emerges from the strange rules of quantum mechanics itself. The many worlds interpretation proposes that every time a quantum particle faces a choice, every possible outcome actually occurs. The universe splits, branching into parallel realities where each possibility is realized. In one world, the electron went left, in another, it went right. This means a version of history exists for every decision you ever made, and for every decision you did not make. Then there is the vision offered by string theory, which suggests a landscape of possible universes, perhaps 10 to the 500 different vacuum states, each corresponding to a universe with a different physical reality. The multiverse is not a single idea, but a spectrum of possibilities, each more vast than the last. We are left to wonder if every possible world is not just a thought, but a place existing somewhere in a reality beyond our own. But if every particle is a note in this cosmic symphony, what is the instrument being played? String theory offers a radical answer. It proposes that the most fundamental building blocks of the universe are not tiny, dimensionless points, but incredibly small, vibrating loops of energy. Imagine an unimaginably tiny string, so small that if an atom were the size of our solar system, this string would be no larger than a tree on Earth. And just like a violin string can vibrate in different ways to produce distinct musical notes, these cosmic strings vibrate in unique patterns. One specific vibration might correspond to an electron, while a different, higher energy vibration creates a quark. In this elegant vision, every particle in the universe, every piece of matter, and every force carrier is simply a different resonant frequency of these fundamental strings. The universe is not a collection of separate particles, but a grand, unified composition played on these tiny, one-dimensional instruments. To make the mathematics of this beautiful idea work, however, the strings require more space to perform their symphony. Our familiar 3 dimensions of space and 1 of time are not enough. The equations of string theory only balance if the universe has 10 or possibly 11 dimensions in total. So where are these extra dimensions? The theory suggests they are compactified or curled up into shapes so incredibly tiny at a scale known as the Planck length that they are completely hidden from our perception. It is like looking at a garden hose from a great distance. It appears to be a simple, one-dimensional line, but if you could shrink down and examine its surface, you would discover it has a second dimension, curled into a small circle all around its length. Our reality may be similar, with 6 or 7 extra spatial dimensions curled into complex, microscopic shapes at every single point in space. This framework holds the potential to be the long-sought theory of everything, a single set of equations that can describe all forces and all matter. The greatest triumph of string theory would be its ability to include gravity, described by the geometry of spacetime, alongside the other fundamental forces, described by quantum mechanics. In this vision, a graviton, the hypothetical particle that carries the gravitational force, is just another vibrational mode of a string. The force that holds you to the ground and the light from your screen would both be manifestations of the same underlying pattern, a hidden harmony written in the vibrations of the smallest things in existence. But these vibrating strings may not be the end of the story. The quest to unite all of physics led to a deeper, more mysterious framework known as M-theory. While string theory offered 5 different versions of a cosmic symphony, M-theory is the grand concert hall that unites them all, revealing they are just different viewpoints of a single, underlying truth. This theory introduces a startling new cast of characters into the cosmic play, entities known as brains. Short for membranes, a brain is not a string but a multidimensional object. A 0 brain is a point, a 1 brain is a string, a 2 brain is a membrane like a sheet, and a 3 brain has the 3 spatial dimensions of our familiar world. Our entire universe, with all its galaxies, stars, and planets, could be one such 3 brain, a vast, floating island of reality. And this island does not float in nothingness. It exists within a higher dimensional space known as the bulk. Imagine our universe as a single, impossibly thin slice of bread within a cosmic loaf. The entire loaf is the bulk, and other slices could be other universes, parallel to our own but separated in a higher dimension we cannot perceive. This mind-bending model offers a compelling solution to one of physics' oldest puzzles. Why is gravity so astonishingly weak compared to the other fundamental forces? A small magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. In the brain world scenario, The answer is that while forces like electromagnetism are confined to our brain, gravity is different. It can leak. Gravity, in the form of gravitons, might be a closed string that can travel through the bulk, its strength diluting as it spreads across the higher dimensions. The force that holds planets in orbit feels weak to us because most of its influence is spilling out into the cosmic loaf, into dimensions we cannot see. This framework also provides a dramatic new origin story for everything. The Big Bang, the moment of our universe's birth, might not have been a singularity in empty space. It could have been a cataclysmic collision. Picture two parallel brains hovering in the bulk, slowly drawn together over eons. When they finally met, the impact would have released an unimaginable firestorm of energy, heating and filling our brain with the raw material for stars and galaxies. Our entire cosmic history could be the aftermath of a single, shattering crash in a higher dimensional reality. And if this is true, then those other brains, those parallel universes, might still be out there, hovering just a tiny distance away in a direction we cannot point to. The laws of physics in those other slices could be completely different, worlds of alien matter and impossible forces, existing forever just beyond the reach of our senses. Are we living on a solitary island, or is our universe just one page in an infinite, multidimensional book? If every particle is just a vibrating string on a multidimensional brain, perhaps the entire cosmic orchestra is running on a computer. The simulation hypothesis takes this idea of a hidden code to its ultimate conclusion, suggesting that our universe is not the base level of reality, but an artificial construct, a simulation created by a vastly more advanced civilization. Think of the video games we play today. A century ago, they were simple dots on a screen. Now they are sprawling, photorealistic worlds populated by characters with complex, simulated lives. If our own technological progress continues for thousands or even millions of years, what kind of simulations might we eventually create? Philosopher Nick Bostrom formalized this intuition into a stark logical argument. He proposes that if any civilization reaches a post-human stage capable of running vast numbers of detailed ancestor simulations, then one of three things must be true. Either no civilization ever reaches that level of technological maturity, or no civilization that reaches it has any interest in running such simulations, or almost every being with our kind of experiences is living inside a simulation. If the first two options are false, if it is possible and even likely that advanced beings would run countless simulations of their past, then the beings in those simulated worlds would vastly outnumber the beings in the original reality. Statistically, you are almost certainly one of the simulated minds. This is not proof, but a simple numbers game. If there is one original reality and a million sophisticated simulations, then there are a million simulated versions of you for every one real version. So, where are you? Some point to the strange rules of our own universe as potential glitches in the source code. Why does the quantum world remain in a blurry state of multiple possibilities until it is observed? Could this wave function collapse be a clever programming trick to save on processing power, only rendering the details of reality when someone is looking? And what about the fundamental limit of space itself, the Planck length, the smallest possible unit of distance? Is this the pixel size of our cosmic resolution, the point where the simulation stops calculating finer details? The philosophical implications are dizzying. If this is a simulation, then the laws of physics are not fundamental truths, but merely the rules of the program, and they could be changed or even break down. The suffering and joy we experience, the entire sweep of human history, could be a form of entertainment, a scientific experiment, or perhaps just background data for some unfathomable purpose. It reframes the deepest questions of existence. Do we have free will, or are our choices predetermined by the algorithms of the simulation? Is there a soul, or are we just particularly complex lines of code? The simulation hypothesis does not offer easy answers, but it forces us to confront the nature of reality itself, leaving us to wonder if we are the players, or merely the characters in someone else's game. The sheer statistical improbability of our universe can lead to a deeply unsettling conclusion. If the cosmos is truly eternal or infinite, then even the most unlikely events are not just possible, but guaranteed to happen somewhere, sometime. This logic births a bizarre and frightening thought experiment known as the Boltzmann brain. It begins with the second law of thermodynamics, which states that the universe, as a whole, is constantly moving from order to disorder, a measure called entropy. The scrambled eggs on your plate will never spontaneously rearrange themselves back into a whole egg. This is the arrow of time, pointing irrevocably toward a future of maximum chaos. Yet, the laws of physics are ultimately based on probability. In any system, there is always a tiny, non-zero chance for a random fluctuation to create a pocket of order from the surrounding disorder. Think of a room full of air molecules. It is overwhelmingly probable that they will be spread evenly throughout the space, but there is an infinitesimal chance that all the molecules will suddenly rush into one corner, leaving a perfect vacuum everywhere else. Now, scale this idea up to a cosmic level. In a vast, old, and mostly chaotic universe, a random fluctuation could, by pure accident, assemble a fully formed, conscious human brain, complete with a lifetime of fabricated memories. This brain, a Boltzmann brain, would flicker into existence for just a moment, believing itself to be a person living in a stable, ordered world. It would recall a childhood, feel the warmth of the sun, and ponder the mysteries of the cosmos, all while floating in the void. Then, just as quickly, the fluctuation would collapse, and the brain would dissolve back into the random chaos from which it came. The paradox this creates is staggering. The probability of a single, self-aware brain fluctuating into existence is astronomically low, but the probability of an entire 13.8 billion-year-old universe with galaxies, stars, planets, and a consistent history forming is infinitely lower. Statistically, it is far more likely for there to be a lone, disembodied brain with false memories than for our vast and seemingly ancient cosmos to be real. This forces a devastating question upon cosmology. How can we trust that our past is real? Our conviction that the world existed before we were born, that dinosaurs roamed the earth, and that ancient civilizations rose and fell, rests entirely on our memories and the physical evidence around us. But a Boltzmann brain would have identical, perfectly detailed memories of all those things, memories that were simply conjured into being a moment ago. The arrow of time, the very foundation of cause and effect, becomes meaningless if the past is just an illusion generated by a random event. This is not merely a philosophical curiosity. It poses a direct challenge to our best models of the universe. If our standard cosmology leads to the conclusion that we are almost certainly Boltzmann brains, then that cosmology is likely flawed. Scientists are forced to search for mechanisms that prevent such fluctuations, or for a cosmic history that makes our ordered universe not just a lucky accident, but a necessary outcome. The search for an answer pushes at the very limits of what we can know, leaving us to wonder if the solid ground of reality is nothing more than a temporary and fragile pattern in an endless sea of chaos. Even the chaos of a random fluctuation is built upon the strange geometry of time itself. Roger Penrose offers a vision of cosmic rebirth so elegant it challenges our very definition of an end. His conformal cyclic cosmology proposes that the universe does not have a final death, but instead undergoes an infinite series of cycles, each one an eon stretching from a Big Bang to an unimaginably distant future. In this framework, the end of time is not a void, but a transformation. Picture our universe trillions upon trillions of years from now. All the stars have long since burned out. Black holes have evaporated away through Hawking radiation. Every particle of matter has eventually decayed into its most basic forms. What remains is a vast, cold, and utterly smooth sea of radiation, a cosmos so empty and featureless that it has lost all sense of scale. There are no planets, no stars, not even atoms to provide a ruler for distance. In this state, the universe becomes conformally invariant. This is a mathematical way of saying that without any structure to define size, the infinitely large and the infinitely small become physically identical. The sprawling, endless emptiness of the far future becomes mathematically indistinguishable from the hot, dense, microscopic point of the Big Bang. The end of one eon seamlessly becomes the beginning of the next, in an endless cycle of cosmic death and rebirth. But how could we possibly find evidence for a universe that existed before our own? Penrose and his colleagues believe they have found a ghostly signature etched into the oldest light we can see. They argue that the collision of supermassive black holes in the previous eon would have sent colossal gravitational waves rippling through spacetime. When our eon began with its own Big Bang, these ripples would have been imprinted as subtle temperature variations on the cosmic microwave background. The stunning claim is that these imprints would not be random. The immense energy of those ancient collisions would manifest as a series of concentric circles, rings within the microwave sky where the temperature variance is unusually smooth. It would be like finding the fossilized ripples from a stone thrown into a pond that existed before time began. This is, of course, a deeply controversial idea. Many cosmologists argue that the patterns Penrose identifies could be statistical flukes, mere coincidences in the complex data. The standard model of cosmology requires no such prior universe, and the evidence for these concentric circles is fiercely debated. Yet the sheer audacity of the theory is captivating. It suggests that the great cosmic cycle of birth and death is eternal, that every ending is a prelude, and that the universe itself is immortal, forever renewing its grand, silent story. This same vision of a cyclical cosmos points to a hidden rhythm, a pulse that might govern everything from the tiniest atom to the vast expanse of thought itself. The law of octaves is a profound esoteric idea, famously articulated by the philosopher Gurdjieff, which suggests that no process in the universe flows in a straight, uninterrupted line. Every development, whether it is the growth of a seed into a tree or the evolution of human understanding, follows a distinct seven-stage pattern, much like the 7 notes of a musical scale. Imagine striking a piano key. The note do resonates, and as you move up the keyboard, you pass through re, mi, and then you arrive at fa. But here is the mystery. Between mi and fa, there is a subtle gap, a semitone interval where the energy of the initial impulse naturally begins to weaken, to deviate from its original course. If nothing intervenes, the entire process will falter, falling short of its intended goal. To continue the ascent to the higher due, an external shock is required, an infusion of energy from a separate source. This is the hidden law governing all energetic transformations. You can see a shadow of this principle in the very fabric of matter. Look at the periodic table of elements. Begin with lithium, a soft, silvery metal. As you move along the row, the elements change in a seemingly orderly progression. But when you reach the eighth element, you do not find something entirely new. You find sodium, which shares remarkable chemical similarities with lithium. This periodicity, this echo after 7 steps, is a faint signature of an octave pattern in the physical world. Gurdjieff applied this law directly to the inner work of human consciousness. He proposed that our initial impulse for self-improvement, a moment of sincere resolution, is the do. We begin with enthusiasm, but when we hit that inevitable inner interval between ma and fa, our will wanes. Distractions arise, old habits reassert themselves, and the initial energy dissipates. To cross this gap and continue our ascent toward a higher state of awareness, we require a conscious shock. This could be a moment of intense self-remembrance, a jarring insight, or the application of a specific, disciplined effort that realigns us with our original aim. This is not a mainstream scientific theory, but it represents a timeless and fascinating attempt to find a single, unified pattern behind the progression of all phenomena. It suggests that the stumbles and plateaus we experience in life are not random failures, but are part of a fundamental cosmic rhythm. The universe itself may be composed of countless intersecting octaves, a grand, silent symphony of development where every leap forward depends on navigating a moment of necessary tension. Sound itself draws patterns in the physical world. If you sprinkle fine sand onto a metal plate and draw a violin bow along its edge, the plate will vibrate. Those vibrations travel through the material, causing the sand to be tossed away from areas of maximum movement and gather along the stationary lines, called nodal lines. What emerges is not a random mess, but a stunning, intricate geometric shape. A low, steady tone might coax the sand into a simple circle. As the pitch rises, that circle transforms, splitting into a perfect cross, then a star, then a complex mandala of breathtaking symmetry. This is cymatics, the science of visible sound. The same phenomenon occurs with water droplets dancing on a speaker cone, forming pulsating hexagons and swirling vortices that look like microscopic galaxies. Each frequency has its own unique visual signature, a hidden architecture made momentarily visible. This is not magic, it is pure physics, a demonstration of how vibrational energy organizes matter. Now, cast this idea across the cosmos. The prevailing theory for the beginning of everything is the Big Bang, a singular, explosive event. But what if that event was not silent? What if it was the first and most powerful note ever struck, a primordial vibration that set all of spacetime ringing? If a simple tone can shape sand into a hexagon, could the complex frequencies of a universe being born have shaped the cosmic web of galaxies? This thought echoes one of the oldest ideas in human history, the music of the spheres. Ancient philosophers like Pythagoras proposed that the planets in their orbits produced a celestial harmony, a perfect, inaudible music based on mathematical ratios, governing the order of the heavens. We now know space is a vacuum where sound waves cannot travel in the conventional sense, but the underlying intuition was profound. It was a recognition that the cosmos operates on principles of resonance and rhythm. Today, quantum physics offers a startling parallel. What are the fundamental particles, if not the tiniest possible vibrations? String theory, as we explored, posits that particles are literally loops of vibrating energy. But even in more standard quantum field theory, Every particle is an excitation, a tiny ripple or vibration in its respective quantum field. An electron is a minuscule strumming of the electron field. A quark is a vibration of the quark field. The entire universe, at its most fundamental level, might be a symphony of interacting fields, a cosmic composition of unimaginable complexity. The hidden patterns we have been searching for, from the spin of an electron to the spiral of a galaxy, may not be written in a silent code of mathematics alone. They might be the emergent, visible expression of a deeper sonic reality, the geometric patterns formed by the enduring music of the Big Bang. This idea of a resonant, learning universe finds one of its most controversial expressions in the work of biologist Rupert Sheldrake. He proposes that the laws of nature might not be fixed and eternal, but more like deeply ingrained cosmic habits. His theory of morphic fields suggests that every kind of thing in the universe, from a molecule of insulin to an oak tree to a flock of starlings, has its own unique non-physical field. Think of it as an invisible mold or a resonant blueprint that shapes its form and guides its behavior. These fields are not made of matter or energy in the conventional sense, but are patterns of information that organize and connect. The most radical part of this idea is morphic resonance, the process by which these habits are formed and strengthened. Sheldrake suggests that the more often a particular pattern is repeated, the easier it becomes for that pattern to happen again, not just in one place, but everywhere. It is as if the universe is learning, and its memory is stored in these fields. A famous example involves laboratory rats. In one classic experiment, rats in a maze in Scotland learned a new route to a food reward. According to morphic resonance, rats of the same breed in laboratories all over the world should then learn that same maze faster, even if there is no conceivable physical connection between them. Sheldrake points to data that seems to show exactly this effect. A drop in the average time it takes for rats to learn the task once it has been mastered by a critical mass of their species. This is not a signal being sent, but a resonance being established, a tuning of the collective blueprint. The theory also aims to explain other puzzling phenomena. How do crystals form so readily? A purely mechanistic view would suggest it is just chemistry and physics. Yet the first time a new complex chemical compound is synthesized, it can be incredibly difficult to get it to crystallize. Once it has been crystallized in one laboratory, however, it suddenly seems to form crystals much more easily all over the world. Conventional science might explain this by saying that microscopic seed crystals are carried on the clothing of scientists or through the air, but Sheldrake offers an alternative. The morphic field for that crystal has been established and strengthened, making its formation a matter of habit for the universe. This presents a direct challenge to the standard model of biology and physics, which sees the universe as a vast, complex machine running on fixed, immutable laws. Sheldrake is proposing a living, evolving universe where the patterns we see are not just the result of blind chance and necessity, but are shaped by a cumulative memory, a resonance across time and space. It is a vision where nature is not a static rulebook, but a story that is still being written, its chapters growing stronger with every repeated word. This quantum hum of possibility finds its source in what seems to be the ultimate silence, the vacuum of space itself. But the void is not empty. It is a seething, bubbling sea of energy, a quantum foam alive with unimaginable activity. This is the zero-point field, the lowest possible energy state of the universe, and it is anything but calm. The reason for this perpetual turmoil lies at the heart of quantum mechanics, in Werner Heisenberg's famous uncertainty principle. This principle tells us that on the tiniest scales, there is a fundamental trade-off. We can never know both the exact position and the exact energy of a particle with perfect precision. There is always a tiny, inherent fuzziness in reality. This uncertainty has a stunning consequence. Even in a region of space that has been cooled to the theoretical limit of absolute zero, where every atom should be frozen in place, there must still be some residual, fluctuating energy. If there were truly zero energy, we would know both its value and its location with perfect certainty, which the laws of physics forbid. So the vacuum must fizz. This zero-point energy is the reason virtual particles constantly blink into and out of existence everywhere, all the time. A pair of particles, one of matter and one of antimatter, can spontaneously emerge from the vacuum, borrowing energy from nowhere for a fleeting instant before they collide and annihilate, paying back the energy debt. This is not just a theoretical idea. We can observe its effects. In a perfect vacuum between two metal plates placed incredibly close together, only certain wavelengths of this quantum flickering can fit. This creates a subtle pressure, known as the Casimir effect, that pushes the plates together, a measurable force generated by the ghostly activity of empty space. This leads to a breathtaking possibility. What if this underlying quantum foam is not just a background hum, but the ultimate canvas of reality? Some cosmologists theorize that our entire universe could have begun as a random, colossal fluctuation in this zero-point field. A tiny bubble of space-time could have tunneled into existence from the nothingness, its immense energy borrowed, and then inflated in the Big Bang to become the cosmos we see today. In this view, every galaxy, every star, and every atom is not merely sitting in space, but is a kind of stable, persistent pattern woven from the fabric of this energetic vacuum. The zero-point field becomes the source of everything, a silent, omnipresent ocean whose ripples give rise to all of matter and energy, painting the entire cosmic picture we call home. This fundamental clash between our two greatest theories of physics plays out in the darkest corners of the cosmos, at the edge of a black hole. On one side stands quantum mechanics, which holds a sacred law. Information, the specific arrangement of particles that makes you and a star, can never be truly destroyed. It can be scrambled, transformed, but never erased from the cosmic ledger. On the other side stands Einstein's general relativity, which describes a black hole's gravity as so intense that it warps space and time into a one-way street. Anything crossing the event horizon, that point of no return, is lost forever to our universe, its information seemingly erased from existence. For decades, physicists believed these two ideas could coexist peacefully. A black hole could simply be a cosmic vault, locking information away forever but not destroying it. Then Stephen Hawking made a startling calculation. He realized that the fierce tidal forces just outside the event horizon could coax pairs of virtual particles from the quantum foam. In a bizarre twist, one particle would fall into the black hole while its partner escaped into space, carrying away a tiny bit of the black hole's energy. This is Hawking radiation. Over eons, this slow leak would cause the black hole to evaporate, shrinking until it vanished completely. And here was the paradox. If the black hole disappears, what happened to all the information about the stars, planets, and atoms that fell in? The radiation Hawking described was purely thermal, a featureless hiss containing no data about what was consumed. The information appeared to be permanently lost, violating a cornerstone of quantum physics. Hawking himself believed, for a time, that information was indeed destroyed. This created a crisis, a fundamental incompatibility at the heart of physics. How could our understanding of the very large and the very small be so catastrophically wrong? The solution may lie in the holographic principle we explored earlier. If our three-dimensional reality is a projection from a two-dimensional surface, then the event horizon of a black hole is not a destructive boundary, but a vast, pixelated hard drive. Every bit of information that falls in is not lost, but is smeared and encoded across this two-dimensional surface, like a cosmic fingerprint. When Hawking radiation is emitted, it is not random. It carries with it, in its most scrambled and subtle form, the data imprinted on that horizon, slowly decoding the black hole's history as it evaporates. The information was never inside the black hole. It was always on its surface. Another radical proposal to resolve the paradox is the AR equals EPR conjecture. It suggests that the entangled particle pairs responsible for Hawking radiation are not just mysteriously linked. They are physically connected by the space-time equivalent of a microscopic wormhole. The particle falling in and the particle flying out are not separate entities sending spooky signals. They are two ends of the same bridge, a tiny tunnel through the fabric of reality. In this view, information does not need to travel or be lost, because it was never separated to begin with. It simply takes a hidden shortcut, preserving the cosmic ledger through the deepest of interconnections. This transforms the interior of a black hole from a prison into a labyrinth of wormholes, a place where information is preserved in the geometry of spacetime itself. The terrifying void becomes a complex network of connections, whispering that loss is an illusion, and that every part of the universe remains forever linked in a web of unimaginable complexity. This same principle of a self-regulating system might be the very signature of life on a planetary scale. The Gaia hypothesis, proposed by scientist James Lovelock with microbiologist Lynn Margulies, offers a radical perspective. It suggests that our entire planet, its living biosphere, its atmosphere, its oceans, and its geology, are all parts of a single, vast, self-regulating system. Earth, in this view, behaves like a living organism. This is not to say the planet is consciously thinking, but that it operates with the intricate, automatic feedback loops of a biological body. Consider the air we breathe. The level of oxygen in our atmosphere has remained remarkably stable at around 21% for hundreds of millions of years. This is no accident. Oxygen is a highly reactive and combustible gas. If its concentration rose much higher, forest fires would rage out of control. If it dropped significantly, most complex life would suffocate. This balance is actively maintained by life itself. Photosynthetic organisms like plants and phytoplankton constantly produce oxygen. At the same time, other biological processes, along with the weathering of rocks and the respiration of animals, steadily draw it back down. Life giveth and life taketh away in a perfect planetary scale dance. The global temperature is another masterfully regulated variable. Our planet has remained within a habitable range for billions of years, even as the sun has grown steadily brighter. How is this possible? One key mechanism involves carbon dioxide. When the Earth warms, plant life flourishes, pulling more carbon dioxide from the atmosphere. This reduces the greenhouse effect and cools the planet. If it cools too much, growth slows, allowing carbon dioxide to build up and warm the world again. It is a natural thermostat, built by and for life. This creates a profound feedback loop where life does not merely adapt to its environment. It actively creates and maintains the conditions for its own survival. The patterns we see in stable ecosystems, in the chemical composition of the sea and sky, are not random. They are the emergent patterns of a complex system in a state of dynamic equilibrium. This idea naturally expands beyond our world. If life and a planet can co-evolve into such a stable pattern here, why not elsewhere? Astronomers now search for distant exoplanets, and the Gaia hypothesis gives them a new blueprint. An exogaia would be a world where the presence of life is not just a faint signal, but a dominant force written across the entire planet. We would look for atmospheres in chemical disequilibrium with combinations of gases, like oxygen and methane coexisting, that should not be stable without a constant biological engine driving them. We would search for a climate that remains stable over geological eons, suggesting a self-correcting system is at work. Finding such a world would mean we have not just discovered life, but an entire living planet, a partner in a cosmic dance of mutual creation. It suggests that the ultimate hidden pattern of a living world is not just the DNA in its creatures, but the enduring, stable rhythm it maintains with its own star. The solid world you perceive is a single thread in an infinite tapestry of realities. This is the startling claim of the many worlds interpretation of quantum mechanics, first proposed by physicist Hugh Everett. It takes the central mystery of the quantum world, the idea that a particle exists in a blur of all possible states until it is observed, and applies that logic to the entire universe. The classic thought experiment of Schrödinger's cat is no longer a paradoxical puzzle, but a literal description of reality. The cat in the box is both alive and dead, not as a potential, but as an actuality in two separate, equally real worlds. The moment you open the box to look, your own reality splits in two. In one branch, you see a living cat and feel relief. In another, parallel branch, a version of you sees a dead cat and feels grief. Both versions of you are real, and both timelines continue forward, forever separate. This branching is not a rare event. It happens constantly with every quantum decision made by every particle in existence. Every time an electron has a choice of paths, every time a radioactive atom could decay or not decay, the cosmos forks. This creates a mind-numbing proliferation of parallel worlds, a multiverse of possibilities where every conceivable outcome actually occurs somewhere. The version of you who took a different job, or who never missed that train, or who said the words you held back, is not a fantasy. They are living their life in a universe that split from your own at the moment of that critical decision. This interpretation paints a hidden pattern of infinite, diverging timelines, a fractal tree of existence growing from every quantum event. It suggests that the path of your life is just one route through an endlessly branching labyrinth, and that the choices you make do not select a single future, but instead spawn entirely new cosmic histories, each one complete and real, forever unaware of the others. This delicate dance of life on a single planet depends on a far more fundamental cosmic imbalance. The very existence of the atoms that make up our world, the stars above, and our own bodies should have been mathematically impossible. Our best models of the Big Bang tell us it should have created a perfectly symmetrical universe, with precisely equal amounts of matter and antimatter. For every proton born, an antiproton should have emerged. For every electron, a positron. And when matter meets its antimatter twin, they annihilate in a flash of pure energy. If the cosmos had been born in perfect balance, every particle would have found its opposite, and the entire universe would have dissolved into a uniform sea of radiation, silent and empty. There would be no galaxies, no planets, and certainly no one to wonder why they are here. The fact that we exist at all is proof of a profound betrayal of that initial symmetry. Somehow, for every 1 billion matter-antimatter pairs that annihilated each other in the primordial fire, one single matter particle was left behind. That 1 in a billion survivor is the reason for everything we see. This is the mystery of baryon asymmetry, and it is the ultimate reason there is something rather than nothing. To understand how this cosmic oversight could have happened, the physicist Andrei Sakharov outlined 3 essential conditions that must have been present in the early universe. First, there must have been a process that violated the conservation of baryon number, meaning the total amount of matter could change. Second, the laws of physics must have been different for particles and antiparticles, a phenomenon known as CP violation, where charge and parity are not symmetrical. And third, this all had to occur outside of thermal equilibrium, in a moment of cosmic disequilibrium where the rules could be bent. For decades, physicists have hunted for the mechanism that satisfied these conditions. The standard model of particle physics does contain a tiny amount of CP violation, but it is far too weak to account for the vast amount of matter we see. It is as if we need a cosmic amplifier to turn a whisper into a shout. One compelling candidate is a process called leptogenesis. This theory suggests that in the searing heat of the early universe, incredibly heavy, sterile neutrinos decayed. In their decay, they violated CP symmetry, producing slightly more ordinary matter particles than antimatter particles. This slight bias in the neutrino sector could then have been communicated to the rest of the particle world, tipping the scales and seeding the universe with the matter that would one day form us. The search for answers continues in massive underground detectors, hunting for the telltale signs of neutrinos behaving differently from their antimatter counterparts. This fundamental imbalance is the ultimate hidden pattern, a single, fragile thread of excess matter that escaped the great annihilation and wove itself into the entire tapestry of the cosmos. Without that 1 in a billion exception, the universe would be a featureless void, its silent perfection forever unobserved. This invisible architecture is the cosmic web, a scaffold of dark matter upon which every galaxy is hung. The evidence for this unseen component is overwhelming, built from decades of observation. We see its ghostly hand in the way stars orbit the center of their galaxies far too quickly. According to the gravity of the visible stars and gas alone, these outer stars should be flung off into the void, yet something with immense gravitational pull holds them in place. We see it in the way massive galaxy clusters behave, their gravity bending the light from more distant objects, an effect called gravitational lensing, which reveals far more mass than our telescopes can account for. This mysterious substance does not emit, absorb, or reflect light, making it completely transparent. We only know it is there by the way its gravity commands the motion of everything we can see. It is the universe's silent partner, making up roughly 27% of all that exists, while the ordinary matter of stars, planets, and people constitutes less than 5%. This means the cosmos is built from a shadow skeleton. When cosmologists run sophisticated computer simulations of the universe's evolution, they start with the near uniform conditions of the early cosmos and let gravity do its work. If they include only normal matter, the result is a disappointing, formless haze. But when they add the gravitational influence of dark matter, something spectacular happens. The simulation naturally weaves itself into an intricate, three-dimensional spiderweb. Vast filaments of dark matter stretch across billions of light years, intersecting at dense nodes, or halos, where thousands of galaxies congregate. Between these threads lie immense, empty voids, cosmic deserts of staggering scale. This simulated web is not a theoretical fantasy. It is a near-perfect match for the large-scale structure we have painstakingly mapped in the real universe. The grand pattern of galaxies observed in sky surveys aligns with this dark matter blueprint. This reveals a profound narrative for cosmic construction. After the Big Bang, slight density fluctuations in the dark matter began to pull more dark matter toward them. Over eons, this created the web's filaments and halos. The ordinary matter, the atoms that make up everything visible, was simply along for the ride. Drawn by gravity, this gas flowed along the dark matter filaments, pooling in the largest halos. There it cooled, condensed, and ignited into the first stars, lighting up the galaxies we see today. We are living in a universe painted in light upon a canvas of darkness, our brightest cities merely tracing the outlines of a hidden gravitational map. Yet this cosmic web of dark matter, this great gravitational anchor for all visible structure, is not the final word on the universe's fate. In the final years of the 20th century, two independent teams of astronomers made a discovery so shocking it overturned a fundamental assumption about the cosmos. They were measuring the distances to extremely far-off supernovae, using these dying stars as cosmic mile markers to gauge how much the universe's expansion had slowed over time. Every scientist expected to find the brakes applied by gravity, a gradual deceleration as the mutual pull of all matter in the cosmos tugged back on the great outward flight. The data revealed the opposite. The most distant supernovae were dimmer than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was stretching the fabric of spacetime itself at an ever-increasing rate, overpowering the collective gravity of everything. This mysterious force was given a name: dark energy. It is the dominant component of our reality, making up a staggering 68% of the entire universe. While dark matter pulls, dark energy pushes. It behaves as a kind of anti-gravity, an inherent property of empty space that generates a negative pressure, forcing the cosmos to expand. The leading candidate for this strange force is something Einstein himself once proposed, and then later discarded: the cosmological constant. This is the idea that the vacuum of space is not truly empty, but possesses its own intrinsic, uniform energy density. With every new cubic meter of space that the expansion creates, more of this vacuum energy appears, leading to even more repulsive force, in a runaway feedback loop that accelerates the expansion forever. The implications of this hidden energy pattern are as profound as they are bleak. It dictates the ultimate fate of everything. In this scenario, the acceleration will continue unchecked. First, the universe beyond our local group of galaxies will recede faster and faster, their light red shifting into invisibility until the entire world beyond our own galaxy vanishes from the sky. Then, as the acceleration grows stronger over trillions of years, it will begin to tear apart the cosmic structures we see today. Galaxies will be ripped from their clusters. Eventually, the gravitational glue holding individual galaxies together will fail, stars scattering into the void. In the final acts, solar systems will be torn apart, planets ripped from their stars, and even atoms themselves will be shredded by the overwhelming force of expansion. The universe will end not with a bang or a crunch, but with a whisper, a cold, dark, and eternally empty void. This is the heat death, the final, frozen pattern dictated by the universe's dominant and most mysterious component. Deep in the cold, dark reaches of the outer solar system, two silent ambassadors began to drift off course. The Pioneer 10 and Pioneer 11 spacecraft, having completed their missions to Jupiter and Saturn, were racing toward interstellar space when tracking data revealed a persistent, tiny, and utterly puzzling deceleration. It was as if an unseen hand was gently tugging them back toward the sun, a force just 10 billion times weaker than the gravity we feel on Earth, yet it defied all predictions. For decades, this pioneer anomaly captivated scientists and fueled speculation. The primary culprit was eventually identified as something remarkably mundane, the subtle but constant push of thermal radiation pressure. As the plutonium in their power generators decayed, it released heat, and the uneven emission of this infrared light from the spacecraft bodies acted like a faint, braking thruster. Yet, for a time, this unexplained drift opened a door to a far more radical possibility, that our fundamental understanding of gravity itself might be incomplete. This idea gave fresh momentum to a theory known as modified Newtonian dynamics, or MEND, proposed by physicist Mordechai Milgram in the 1980s. MEND suggests that Isaac Newton's famous law of gravity, and by extension Einstein's theory of general relativity, breaks down at extremely low accelerations, the kind experienced in the faint gravitational fields at the edges of galaxies. The core evidence for MEND lies in those perplexing galactic rotation curves. Stars orbiting a galaxy should slow down as they move farther from the center, just as Pluto moves more slowly around the Sun than Earth does. But observations show that these outer stars maintain high speeds, a fact conventionally explained by the gravitational glue of invisible dark matter. MEND offers a different solution. It proposes a new, hidden pattern in the fabric of gravity itself, a fundamental acceleration scale below which gravity behaves differently. In this framework, the force of gravity does not fade with the square of the distance as neatly as we thought. It transitions to a new rule that provides an extra gravitational tug in the outskirts of galaxies. This single modification can perfectly match the observed rotation of hundreds of galaxies without requiring a single particle of dark matter. The implications are profound. It suggests that the cosmic web of dark matter we think we see mapped across the universe might be a grand illusion, a misinterpretation of gravity's true hidden behavior. For MEND to be a complete theory, however, it must be made compatible with the towering success of Einstein's relativity. This has led to the development of relativistic extensions, like tensor vector scalar gravity, which attempt to weave MEND ideas into the very geometry of spacetime. The battle between these competing explanations, dark matter versus modified gravity, is one of the greatest in modern cosmology. Does the universe contain a shadowy, invisible substance that dictates its structure? Or have we simply been reading the most fundamental force incorrectly all along? The Pioneer anomaly itself may be solved, but the deeper question it raised still echoes. Perhaps gravity holds a secret scale, a hidden pattern that only reveals itself in the deepest quiet of space, waiting to rewrite the laws of physics. That ghostly tug on the Pioneer probes reminds us how a single anomaly can challenge everything we think we know. But another, far more famous signal from the void did more than challenge our physics. It challenged our cosmic solitude. For 72 seconds in August 1977, a giant ear aimed at the stars heard something that should not have been there. The Big Ear radio telescope at Ohio State University was engaged in its methodical, silent sweep of the sky, part of the search for extraterrestrial intelligence, when its printout recorded a sequence of characters that made researcher Jerry Amon circle the data in red pen and write one word beside it: wow. The signal was not random static. It was a powerful, focused burst of radio waves concentrated in a narrow band of the spectrum, a band that is naturally quiet, reserved for the faint whisper of interstellar hydrogen. This is precisely the channel an advanced civilization might use to send a beacon, a clear signal designed to stand out against the cosmic background noise. It came from the direction of the constellation Sagittarius, rising and then falling in intensity over exactly 72 seconds, the exact duration the Big Ear would expect as a point source drifted through its stationary, football field-sized receiver. It was a perfect match for the signature of an artificial interstellar transmission. And then it was gone. For decades, astronomers have pointed every available instrument toward that same patch of sky, listening with ever more sensitive technology for a repeat, for a follow-up, for any hint of another patterned hello. The silence has been absolute. This singular, unrepeated event has fueled one of the most enduring theories in the search for alien life, that the WOW signal was a genuine, fleeting message. Its brief nature is a large part of the mystery. What could it have been? Perhaps it was not a continuous broadcast, but a targeted burst, a lighthouse beam sweeping across the galaxy, and for 1 minute and 12 seconds, we happened to be in its path. Our planet sailed through the signal like a ship through a searchlight, illuminated for a moment before returning to the dark. Or maybe it was a one-time event, a powerful mobilization of energy for a purpose we cannot fathom, a cosmic snapshot sent once and never again. The intent behind such a message is even more perplexing. Was it a deliberate hello, cast into the deep in the hope that someone, someday, would be listening in the right place at the right time? Or was it an accidental leakage, the equivalent of a military radar sweep or a burst of energy from an immense interstellar engine, a signature of technology so advanced its byproducts are as powerful as our most focused attempts to communicate? The WOW signal remains a haunting possibility, a single, elegant pattern etched into the radio silence, a suggestion that we are not alone, and a reminder of how vast and quiet the cosmic ocean truly is. The deep silence following the WOW signal leaves us contemplating our solitude, but the cosmos also sends more violent messages. In the early morning of June 30th, 1908, over a remote Siberian forest near the Tunguska River, a fireball tore across the sky. Moments later, a blast of heat and force flattened 80 million trees across 800 square miles. The shock waves circled the globe twice. Reindeer were incinerated where they stood, and the night skies over Europe glowed for weeks, bright enough to read a newspaper outdoors at midnight. The energy released was equivalent to a large hydrogen bomb, between 10 and 15 megatons. Yet, when expeditions finally reached the epicenter decades later, they found no crater. The ground was scorched, and trees were felled in a vast radial pattern, pointing outward from a central point high in the atmosphere. The leading scientific explanation is a cosmic airburst. A stony asteroid, or perhaps a fragile comet, roughly 200 feet across, entered Earth's atmosphere at hypersonic speeds. The intense pressure and heat caused it to explode some 3 to 6 miles above the ground, releasing all its colossal kinetic energy at once in a flash of superheated gas. It was a natural, if terrifying, event. Yet the utter strangeness of the event, its scale, and its remote location have fueled more speculative ideas for over a century. What if it was not a rock, but a microscopic black hole, a pinprick of primordial density left over from the Big Bang, passing straight through our planet like a bullet through smoke? Or perhaps it was the catastrophic failure of an alien spacecraft's propulsion system, a single, desperate moment of interstellar travel ending in a cataclysm on a primitive world. While these fringe theories lack evidence, they speak to our deep desire to find meaning in the random violence of the cosmos. The Tunguska event stands as a stark monument to a cosmic coincidence, a reminder of how a single, rare object from the depths of space can irrevocably alter a world. This forces a profound question about hidden patterns. Is the timing of such impacts truly random, a chaotic game of celestial billiards? Or are there subtle, predictable cycles buried in the gravitational pull of the planets and the oscillations of our solar system through the galaxy? Some researchers have proposed that comet showers might be triggered as we pass through the dense plane of the Milky Way, or that gravitational nudges from Jupiter could periodically send debris from the asteroid belt hurtling inward. Understanding this pattern is not merely academic, it is the foundation of planetary defense. How often does an event of this magnitude occur? Current estimates suggest a Tunguska-level airburst happens every few hundred years. A larger, civilization-ending impact, like the one that wiped out the dinosaurs, is a once-in-a-100-million-year event. This is the hidden rhythm of cosmic intervention, a pattern of rare but inevitable encounters. Our continued existence depends on our ability to read this chaotic code, to map the near-Earth objects that share our orbit around the Sun, and to develop the technology to nudge them aside. We live on a moving target in a cosmic shooting gallery, and the next message from the void may not be a whisper, but a bang. Far beyond the orbit of Neptune, in the deep freeze of the solar system's twilight zone, a group of small, icy worlds are behaving strangely. Their elongated orbits are not randomly oriented as we would expect, but instead seem to be clustered together, as if herded by an unseen shepherd. This peculiar alignment is the strongest clue we have for a hidden giant, a hypothetical world several times more massive than Earth, which astronomers call Planet 9. The gravitational pull of this unseen perturber would be the invisible hand guiding these distant objects, explaining why their closest approaches to the Sun are grouped in one part of the sky, and their orbits are tilted in a similar way. Without such a massive influence, the random tug of the known planets should have scattered their orbits into a chaotic jumble over billions of years. The very fact that we see this distinct clustering is a powerful argument that something big is out there, sculpting the architecture of our solar system's outer frontier. The hunt for this world is a monumental challenge. Its proposed orbit is so vast that it could take between 10,000 and 20,000 years to complete a single journey around the Sun. At such an incredible distance, it would reflect virtually no sunlight, making it a billion times fainter than what we can see with the naked eye. Astronomers are using the world's most powerful telescopes to scan the sliver of sky where its orbit is predicted to be, looking for a single, faint pixel of moving light against a backdrop of stationary stars. But what could this world be, and how did it get there? One compelling theory is that Planet 9 is a primordial core, a world that began to form in the early solar system, but was gravitationally kicked outward by Jupiter or Saturn before it could grow into a proper gas giant. Another, even more dramatic possibility is that it is a rogue exoplanet, captured by our Sun's gravity after being torn free from its own star system in the chaotic infancy of the galaxy. This would mean our solar system is not a closed family, but an adoptive one, harboring a wanderer from the interstellar deep. The discovery of Planet 9 would be more than just adding a new world to our charts. It would fundamentally rewrite the story of our cosmic neighborhood, revealing a hidden pattern of gravitational influence that has been shaping the outer darkness all along. This profound silence from the cosmos carries a name, the Fermi paradox. Given the sheer number of stars and planets, the universe should be teeming with intelligent life, a vibrant galactic community. So where is everybody? One terrifying answer is the Great Filter, a hypothetical barrier in the evolution of life, so difficult to overcome that it silences nearly every civilization that approaches it. This theory suggests a hidden pattern of cosmic evolution, a developmental wall that most life forms simply cannot scale. The critical question is where this filter lies in the timeline of existence. Is it behind us, or is it waiting for us in the future? If the filter is behind us, it means we are among the impossibly rare few who made it through a key evolutionary bottleneck. Perhaps the spontaneous origin of life itself was the miracle, a 1 in a trillion event. Or maybe the leap from simple prokaryotic cells to complex eukaryotic cells, a process that took over 1 billion years on Earth, is the true filter, a biological hurdle that almost no other world manages to clear. In this scenario, we are the first, or perhaps the only, conscious beings in our galaxy, lonely pioneers in an empty cosmos. The silence is not ominous. It is simply the sound of a universe where life almost never gets this far. The alternative is far more unsettling. What if the Great Filter lies ahead of us? This version of the theory suggests that the path to advanced technology inevitably contains a self-destruct mechanism. Perhaps once a species discovers the power of the atom, it is only a matter of time before it turns those weapons upon itself. Or maybe the creation of artificial intelligence always leads to an uncontrollable intelligence that extinguishes its creators. It could be that any civilization advanced enough to communicate across the stars is also advanced enough to create ecological or biological disasters it cannot contain. In this light, the eerie silence is a cosmic graveyard, a warning that no one makes it past the technological adolescence we are now experiencing. We look up at the quiet stars and wonder if we are listening to the aftermath of countless civilizations that reached our stage and then, suddenly, went silent. This theory reframes our entire existence. Our successes in science and engineering are not just achievements. They are steps toward a test we cannot see. Every crisis we navigate, from climate change to the threat of nuclear war, might not be a unique challenge, but a universal rite of passage that almost everyone fails. The Great Filter is the ultimate hidden pattern, a law of cosmic sociology that dictates the rise and fall of intelligence. It asks us the most important question we will ever face. Are we the exception, having already passed the universe's greatest challenge, or are we, like so many others before us, simply on the path to becoming another silent date, a point in the void? Sometimes the universe writes its patterns in the faintest of glows. Long after sunset or just before dawn, a subtle pyramid of light can sometimes be seen reaching up from the horizon, following the same path across the sky that the sun and planets travel. This is the zodiacal light, a soft, ethereal luminosity often mistaken for the first hint of morning. It is not the glow of distant cities or a trick of the atmosphere. This light is the scattered reflection of our own sun on a sea of cosmic dust. These are not just stray motes floating in the void. They form a colossal, lens-shaped cloud that envelops our entire solar system, centered on the sun, its particles concentrated along the flat plane where the planets orbit. This is the zodiacal dust cloud, and it is a living, dynamic structure. The origin of this fine, powdery grit is a constant, silent bombardment. It comes from the gradual disintegration of comets, as their ices vaporize and release trapped dust during their journeys around the sun. It comes from the occasional, violent collisions between asteroids in the belt beyond Mars, grinding rocks into fine powder. This dust represents the ongoing construction and demolition of our solar system, a process that has continued for 4.5 billion years. Every day, tons of this material, most of it no larger than grains of sand, rains down into our atmosphere, a gentle, cosmic snowfall that has been falling since the Earth was young. This hidden reservoir of dust is not unique to us. Around other stars, astronomers can detect similar, but often vastly larger, disks of debris. These extrasolar zodiacal clouds are so thick with ground-up rock and ice that they outshine their parent star in infrared light, revealing a system teeming with the raw materials of planets and the aftermath of colossal collisions. Our own faint glow is a quieter version of this universal process. It paints a picture of planetary systems not as static, finished sculptures, but as dynamic, dusty construction sites. The zodiacal light is more than a beautiful illusion. It is the visible signature of a slow-motion cosmic dance, a reminder that our solar system is still breathing, still building, and still being shaped by a gentle, perpetual rain from the depths of space. That profound silence was broken, not by a signal, but by a visitor. In October 2017, a telescope in Hawaii detected a faint point of light moving at incredible speed. It was the first object ever observed from beyond our solar system, a cosmic wanderer from the void between stars. They named it Oumuamua, a Hawaiian word for a messenger from the distant past. Its trajectory was a hyperbola, a path that meant it was just passing through, a single, fleeting tourist in our celestial neighborhood. But its strangeness only grew the more we looked. Its brightness varied dramatically, suggesting it was tumbling end over end. Calculations revealed its shape was unlike any asteroid or comet we had ever seen. A bizarre, elongated sliver, perhaps 10 times as long as it was wide, like a cosmic pancake or a discarded cigar. Then came the true mystery. As Oumuamua sped away from the sun, something was wrong with its path. The gravity of our star and planets could not fully account for its movement. It was accelerating ever so slightly as it departed. This non-gravitational acceleration is exactly what comets do when they are close to the sun, as their surface ices heat up and vaporize, jetting out gas and dust to form a visible tail. This outgassing acts like a natural rocket engine. Yet when every telescope turned toward Oumuamua, they saw no tail, no cloud of gas or dust, no coma whatsoever. It was a rocket with no visible exhaust. The mainstream scientific explanation holds that it was a comet after all, but a very strange one. Perhaps it was made of very pure, solid hydrogen ice or nitrogen ice, which could have outgassed in a way that left no dusty residue for our instruments to detect. Or maybe it was a fractal-like aggregate of dust, a cosmic dust bunny so porous and light that gas could seep from its entire surface without forming a concentrated jet. This would explain the acceleration without a tail, a silent, invisible puff of propulsion. But the object's extreme shape remains a puzzle for natural formation. Harvard astronomer Avi Loeb offered a more radical interpretation. He asked if Oumuamua's properties might be better explained as a piece of advanced technology. Its unusual flatness and brightness could be consistent with a light sail, a thin, reflective sheet designed to be pushed by the radiation pressure from stars. The slight acceleration as it moved away from the sun could have been the result of solar radiation pushing on this vast, thin surface. In this scenario, we were not looking at a weird rock, but at a derelict probe, a piece of discarded alien engineering adrift in the galactic currents. Whether an exotic shard of nitrogen ice or an artifact from a distant civilization, Oumuamua challenges our assumptions. It suggests that the hidden pattern of interstellar space is not one of emptiness, but of a constant, quiet traffic in strange objects. Our solar system may be continually visited by such wanderers, most too small and dark for us to ever see. This one we caught by chance, a single data point that forces us to wonder what else is out there, silently passing through our backyard, carrying secrets from stars we will never reach. Even the most stable structures in our world hold a secret rhythm, a hidden beat that defies the quiet sleep of equilibrium. The atoms in a diamond are locked in a perfect, repeating lattice in space, a symmetry so absolute it seems timeless. But what if matter could crystallize in time itself? This is not science fiction, it is the reality of time crystals, a new and bizarre phase of matter first imagined in 2012 and now breathing in laboratories around the world. A time crystal is a quantum system that oscillates, not because it is being pushed, but because that is its most stable, lowest energy state. Think of a clock that ticks forever without any batteries, or a ring of atoms that perpetually flips its magnetic orientation in a perfect, unending rhythm, all while sitting in its quantum ground state. It does not consume energy, it does not wind down, it just pulses, a silent metronome beating against the flow of time. This behavior shatters a fundamental symmetry physicists have long held sacred time translation symmetry. This is the idea that the laws of physics are the same at every moment, that an experiment performed today should yield the same result as one performed tomorrow. But a time crystal breaks this rule. Its stable state is not uniform across time. It has a preferred tick, a moment in its cycle that is fundamentally different from the others, creating a structure that repeats periodically in the fourth dimension. How is such a thing possible without violating the conservation of energy? The secret lies in a kind of quantum frustration. In the lab, researchers create a system, often using a chain of ions or dense clouds of atoms, and give it a precise one-time kick. In a normal system, this kick would cause chaotic motion that eventually settles into stillness. But in a carefully tuned time crystal, the components become entangled in such a way that they cannot settle. They are trapped in a dance, forever returning to their starting configuration only after two or more kicks, a subharmonic rhythm that proves their unique, non-equilibrium nature. This discovery opens a window into a hidden cosmos of organization. If matter can assume such a phase here on Earth, what strange crystals of time might exist in the universe's most extreme environments? Deep inside a neutron star, where matter is crushed to unimaginable densities, the nuclear material may be structured as a time crystal, its components oscillating in a locked, eternal rhythm under immense gravitational pressure. Or perhaps the seething vacuum of space, with its constant pop of virtual particles, hosts fleeting, microscopic time crystals. These non-equilibrium phases represent a fundamental new pattern, a way for matter to find order not in spite of chaos, but within it. They show us that the cosmos may be filled with silent, perpetual motions, clocks that have been ticking since the beginning of time, their hidden rhythms woven into the fabric of reality itself. From the infinite spirals of the Fibonacci sequence to the silent question of the Fermi paradox, we have journeyed across a cosmos woven with codes. We have stood at the edge of black holes where information plays hide and seek, peered into the quantum foam from which everything flickers into being, and wondered if our entire reality is but a shadow on a distant wall or a simulation running in some unfathomable computer. We have traced the invisible hand of dark matter, felt the repulsive push of dark energy, and listened for whispers from visitors like Oumuamua. These 30 theories, from the deeply scientific to the profoundly philosophical, are not just answers. They are testaments to a single, driving human impulse, the need to look into the starry void and find a story. It does not matter if every idea is proven correct. The value lies in the search itself, in the act of reaching for a map in the darkness. This quest pushes the very boundaries of what we can know, forcing science and philosophy to dance together in the grand ballroom of the unknown. The universe may not give up its secrets easily, but in our relentless quest to find its hidden patterns, we are, in fact, writing the most beautiful pattern of all, the story of our own curiosity. Now we turn the question to you. Which of these theories captivates your imagination the most? Share your favorite in the comments below, and if you are hungry for more journeys into the unknown, be sure to subscribe for our next deep dive into the